Gergely from AI Motive, and I'm a kind of stuntman here because Victor Janesh, who is the editor of the NNEF specification, was unable to come, and he asked me to deliver this presentation since I'm anyway here at EVS, so I was happy to do that. I have very little information how deep your knowledge and how diverse your knowledge about NNEF, so excuse me if I start with some very basic stuff. I will describe what is NNEF, what was the motivation behind, what is its current status, what are the plans, and how it is used in the industry and also at AI Motive. And after that, I will just show you a 5 minutes, very simple command line demonstration how one can use the toolkit and how the specification looks like. I also set up a small demo in the background. If in the break you can go and see. That's a practical implementation how we use NNEF to export and run our neural networks on embedded hardware on the chip that we designed. So just quickly about NNEF. NNEF is a neural network exchange format. It has been initiated by AI Motive. I'm from AI Motive, a self-driving software company based in Hungary, Budapest. And after a short brainstorming, exploratory phase, we initiated the standard. And there have been a working group set up at Khronos, and through many multiple iteration and change of ideas, finally, in November 2018, the first version of the specification has been released. Since then, many companies has joined the effort, and it's of course an ongoing effort to make it further, to release new versions. But why it is necessary, I will explain in a moment. Just a couple of sentences about AI Motive, so how we come to the picture. As I mentioned, AI Motive is a company in Budapest, Hungary. Currently we are 220 people. We are a software company developing software for self-driving and ADAS functionalities. We do full stack perception, motion planning, decision making, control for the ADAS self-driving part. We also develop a simulator environment that helps us testing the self-driving software, and we also have a hardware department. They are responsible for developing and constructing neural network inference engines, accelerators in an embedded environment. And why these three activities, so software, self-driving, software simulation, and hardware? It seems a bit too much for a small company like us, but these three areas of development really helps each other, and there is a very close communication between those groups, and that's why we managed to make these solutions up to a very nice quality. And as we have been working with different kind of deep learning frameworks, as just like many of you, we experience that they are changing very fast. They have different conventions, different formats, different interfaces, and also we had to port those results into different kind of compute platforms. So we got a many-dimensional connection matrix, which is very difficult to handle in practice. So we came up with the idea that it would be nice to have a common exchange format between these frameworks, and this common exchange format, as it's kind of obvious, could be used to implement a common language between the software frameworks, inference engines, training engines, and then there is no need for this multi-dimensional support for each company. These frameworks are, in principle, at the high level, they are seems to be different, and they have pros and cons depending on the use case. But at the low level, when they produced a neural network or they produced an execution graph, in fact, they are using very similar operations and very similar considerations. And that is what made us thinking about that these similar, conceptually similar operations can be described with a relatively simple language, with a relatively simple specification. I just put some example here. So there are differences in parameterization, output shape, padding, or representations, output value computation, but there are similarities which can be included into the framework, and there are differences which must be excluded. So we wanted to keep the NNEF framework as general and as wide as possible. What is the design philosophy? So the first sentence is exactly what I just said. It should convey all the relevant information from the deep learning frameworks to inference engines. So to ship as many information from the framework to the inference engine as possible. However, shipping everything is difficult and would require maintaining a lot of addition and extension. So this is always a compromise, what is worth to include and what is not. This exchange format must be platform independent. I think there is no need to explain this. What is really difficult to keep it flexible, still robust enough. So if you make your exchange format or if you make an interface too flexible, then it will change a lot. You will have to support a lot of staff features for backward compatibility, and you result a lot of future work for you. If you include too few feature or too few information, then it will be unusable. So this flexibility, extendability is really something that must be carefully maintained through the development of the standard. Easy to consume by compiler optimization tools. So these are softwares eating software data. What easy means is interesting, but the idea was here that even for humans, it should be a really easily understandable format, both the file format and both the concept, and also it should be easy to implement parsers, compilers that can process this format without big problems. And of course, in embedded AI inference, quantization has an important role. So we also talked about how to support quantitization and which part of those techniques should be included into the exchange format and which one should be left out. Support in network architectures, as I mentioned, every week there is some strange network architecture popping up in different researches. However, sooner or later it turns out that those architectural magics can be decomposed to maybe a bit higher number, but already known layer types. And at the end, usually those architectures are using the same 5 or 10 well-known layer types and operations. So we are, of course, must support them, and we also should be very careful when to include and how to include this new kind of exotic layers or exotic activation functions or kernels. But of course, what was obvious that the following tasks like image classification, semantic segmentation, object detection, video processing must be supported because these are the tasks typically performed by embedded systems. But it does not impose too much constraints on the standard itself. It's just an example to typical use cases. What was also obvious from the beginning that fully connected networks, multi-layer perceptors, autoencoders, convolutional networks, recurrent neural networks must be supported because they have a very well-established use case in the industry. They are used every day in many devices. So the architecture and the data flow of those kind of networks must be supported by the standard. We have been focusing on inference, so computing in an embedded environment, computing on the edge, and with an eye on optimizing inference. However, nothing prohibits us to use the same standard for training. A couple of simple layer type must be added to the standard, and it can be used also for training purposes. So these were the design philosophies, and as I mentioned, through multiple iterations and through a wide collaboration of the Khronos group members, by now there is an implementation and a first version of the specification. There were also other considerations that we made. For example, that it would be really nice to have a functionality that allows us to easily validate the description, the network description. So check for syntactic and semantic errors, and a parser or the compiler should really be able to identify early on whether there is a misdefinition or inconsistency inside the network definition. What I mean here is, for example, if the output shape of one layer is different than the input shape of the other layer, then the compiler should throw a warning or an error, and things like this. What is included into the standard? So I know I mentioned a lot of different area of this field. But the goal of NNEM aims to abstract out the network description. So it's not trying to describe, for example, the optimization algorithm or the loss function, but it's really the network architecture and the quantization information, and there is a possibility to export the weights, and not only the architecture, but for example, the weights and the activations of a trained network. A distilled set of frequently used operations, I think this is also quite understandable. As I mentioned, we don't want to update the specification every week with new features, new specification, but we have to understand in this rapidly changing field that what will be usable on the long term, what will be important on the long term, and what will be forgotten in half a year. And those features must not be included into the specification. A simple syntax, that is of course a very good feature. And this syntax, we have been focusing on a text format, human readable format, for ease of understanding. But of course this can be easily transferred to a binary format, and that's not really a problem. Maybe I'm not going to the details of this description. What may be worth to mention is that the NNEF architecture description supports a simplistic, I would call them atomic layer types or atomic operations, but it also supports composite, compound layer types. And depending on how the hardware implementation of a hardware inference engine supports these layer types, those compound layer types can be either interpreted as a whole, as they are, if it is supported on the hardware side, or can be so-called lowered, decomposed to simpler set of layer types, and exported in that way to the hardware. A predefined set of primitive operations like element-wise activation, pooling, normalization, etc., the well-known operations in AI training. As I mentioned, it's not only about the structure, so the first primary purpose was really to describe the structure. However, when you have a already trained network, it is essential to be able to ship the weights along the structure to the inference engine. And the parameters of the tensors are stored in a separate format. Those are in binary format and in different files. I will show you soon. But it's really simple, so the syntax is kind of trivial. For human readability, if I have, for example, a ResNet or I have an AlexNet, everything, all the NNEF description is contained in a directory. The different layers are stored in different files. That allows you to easily read, and you don't have to parse files with hundreds of thousands of lines. And each network architecture descriptor file has a corresponding data file where the weights of the corresponding layers are stored. the data file is binary, the architecture file is architecture description file is a text file. Everything can be, of course, zipped up in a single file and is handled by the NNEF tools, but that's only a small technicality. As I mentioned, there is many different kind of quantization techniques when it comes to training or inference. We thought that it would be very nice to catch some of this essential information, but of course it's almost impossible to accommodate to all the use cases currently used. So how to transfer your 12-bit or floating point representation into an 8-bit representation, how to normalize it or resample that layer by layer. So not all the aspects of this kind of techniques is presented in the NNEF format, but there is quite some information about what level of quantization the different layer types are using. As I mentioned, so the primary purpose when we started this is to have a functionality which allows one to transfer the different deep learning frameworks output into a common representation. And for example, Caffe, TensorFlow, or PyTorch were such. And we developed simple tools for this conversion. I will show you in a minute how it works. And you can convert, for example, TensorFlow to NNEF and the other way around. Of course, maybe the TensorFlow description contains a much wider set of possible layer types or possible activations. And the NNEF standard may be a bit more narrow. So only those activation types or layer types can be transferred to NNEF, which are, of course, supported by the standard. However, if the translator, if the parser script finds a layer type which is not supported by NNEF, it is still possible to specify custom user-defined layer types, which are kind of extension to the standard and can be used locally. What are the tools? I will show you this GitHub repository soon. The tools composed mainly transforming tools, how to transform one format to the other, back and forth. It contains also validation tools, so tools which are validating your description. And these transform tools also, I haven't mentioned that, but it is possible to transform, for example, a TensorFlow PB file into an NNEF, but you can also transform the TensorFlow Python description, the Python file itself, into an NNEF format. You don't have to export that. I will show you an example soon for that. There is a lot of possibility and a lot of direction how one should develop further such standard. We are also thinking about specification additions, so what kind of new AI properties, AI parameters should be, neural network parameters should be represented, defined by the NNEF standard, but also there will be need for some visualization tools or transformation tools, which makes the usage of the NNEF format more user-friendly. Also, it would be very nice that, as I mentioned, different inference engines, different hardwares are using different number representation precisions, or maybe different fast mathematics. So there is a need for a kind of conformance test. What I mean here is that if there is an NNEF neural network description with the architecture and with the weights, it would be very nice to have a conformance test, which is about to compare the result of an inference engine, result of a hardware executed inference with a predefined set of output. And through the comparison of this predefined pre-calculated results and the inference engine results, one can have a stamp on its hardware that this hardware is conformant with NNEF specification, I don't know, 1.1. So this would be very important because it is one thing how the standard is defined, and the other thing is how an inference engine is implemented in practice, really, on the hardware. There is always a discussion and a question, what is the relationship between NNEF and ONNX? What I can tell you about this is that in practice, from a technical point of view, we don't see much difference. So as I mentioned at the beginning, at the low level, they are very much the same. There is not much magic, so they are supporting the same kind of layer types, the same kind of operations. ONNX is a bit wider, so it's a more faster developing standard. It's more flexible. Almost anybody can initiate the addition of a new feature. So it's very rapidly following the state of the art. It's very good for prototyping. While NNEF, we believe, is a kind of more settled down for the long term. And also the development, the governance model of the standard itself is more formalized. So people can participate, they can vote for new features, they can understand better what will be important on the long term, what will not be. So it's more like a long-term, slowly changing industrial standard, while ONNX is, in our view, is more like a quickly following state-of-the-art prototyping standard. As I mentioned, anyone who wishes to review the NNEF specification can join the advisory panel. And there is a lot of examples available on GitHub, how it works, how it looks like. There are example files for network architectures, both in TensorFlow, NNEF, ONNX format. And this is now quite open and can be used and tested by anybody. Yes, so just in 5 minutes, I don't know whether anybody has question now or maybe during the demo. What I would like to show you is really how simple to use it or how it looks like in practice. So I put a small cheat sheet here for myself. I just exercised this yesterday evening. And so I just created a new directory, and we go through on the first couple of lines. I will not show you everything because it's quite repetitive and really easy to understand. So what I'm doing now is cloning out from GitHub the NNEF tools repository, which contains different tools and example files. I hope it will be downloaded soon. It doesn't seem so. Okay, but I think this is a command that everybody is familiar with and everybody knows. I have a pre-checked version of the NNEF. Let's wait. Okay, it's almost there. Okay. Okay. So an NNEF tools directory have been checked out. And to install it and to make it available in Python, all that you have to do is go to parser and then type in, execute the install command. There is a usual setup.py, setup.py. Here, and it installs, compiles the module and makes it available in user space if you define the --user command. So just to check whether the installation went fine, we start and try import NNEF, and we imported a new NNEF module without problems. So in the examples directory, you find an alexnet.txt file, which is an example of the architectural text file format based description of the AlexNet network. I think the naming conventions, the words and the numbers are quite self-explanatory. I'm not going to explain all of those, but this is the layer by layer definition of the AlexNet network, and in an NNEF format. And what we would like to do, for example, in the next step, is to validate whether the description is valid or not. So I just executed this command below, validate.py. I specify the input file, which is the alexnet.txt. It echoed the file, so it just put the content of the file to the screen, and it returned with no error, which means validation succeeded. So all the layer definition is consistent. There is no syntactical, semantical error in the file. This is a very simple, very useful tool to check your file definition. Just another example, if I specify --shapes, then also a bit more advanced validation will happen. It will check whether the shapes of the output shapes of one layer is consistent with the input shapes of the other layer of the following layer, and it also works. So it really doesn't require too much explanation. Maybe I will show you just a conversion demo, and that will be the last one. Let's try to download this file. Maybe this will be very long, so let's see if it is still at TMP. Yes, I downloaded it yesterday, so unfortunately not. Okay, then, sorry, I was not expecting the network to be so slow. I skipped to the next one. It was an ONNX description of the SqueezeNet, and I wanted to transform it to an NNEF format, but maybe I just go to the next one and show that. That will be a very simple transformation. So let's find the file. Okay, no, I'm sorry, I stop here now. I cannot download and don't find the NNEF format, but I will be happy to share this cheat sheet with you. I think it's was only about just executing this command, and the commands are quite self-explanatory, so you have to specify an NNEF input file or TensorFlow input file together with its format, and you have to specify the output NNEF format name, that's it, and it just works. But I know I cannot download an NNEF file. Sorry?
You can connect to my hotspot, it's pretty fast.
That can be also a solution, but I think I'm run out of time, as you wish, but it's really not a rocket science, everybody can do this. Okay, we can. What's the name of the?
7 cents mobile.
Thanks.
Password is 7TH.
With typing or with number?
Number. 7TH. Cents. I said otherwise you won't be able to.
Okay. You saved the show. Now let's see whether you can download. It's much better. Thank you. Yes, so thank you very much. So I downloaded the tarball, which is the ONNX description. Here it is, the model.onx, which is a binary file, but still you can catch some of the layer types. And I show you now how to convert this format to NNEF. So if we go back to here to the checked out Git repository, then we can run the convert command. And fix the path. So NNEF tool convert.py, input format is ONNX, input model is /tmp/EAA/squeezenet/ model.ONNX. Output format is NNEF and compress. The default behavior is that it produces the file, the output file, in the same directory as the input file was, and the -- compressed means that it compressed the it created a tarball. So let's see whether it's there. Yes, model ONNX NNEF.tgz is the newly created file. Let's see now what is inside. So just to be safe, I put it into a different directory. So I copied into the directory T. I extract it, and you see, as I mentioned, the different layers are stored in different files. These Fire 2, Fire 3, Fire 4, and the corresponding weight files are also there. And let's see the architecture description file. This is graph.nnef, and here it is. Here, how it looks at an NNEF format. This is the SqueezeNet network. So maybe just for comparison, if we want to see how it looks. And NNEX, the comparison is not that meaningful, but as you see, one is binary, the other one is a text file. All the other exercises have the similar level of complexity, so I could convert other files to this format as well. And maybe I show you if I manage another demo. Yes, so just an example. As you are familiar, probably, if I have a TensorFlow AlexNet definition, that looks like this. This is a typical network architecture definition in Python in TensorFlow. So I have the AlexNet def function and also the AlexNet inference function defined in a TensorFlow format. In order to have this network in an NNEF format, it's not necessary to export it. Either you can export it into a .pb file, or you can use directly this file, this Python file, to create your NNEF description in the same way. So in this directory, I have alexnet.py down below, and I also have the checkpoint file. So this was, for example, in the middle of a training, and I had saved a checkpoint. So I can use these two files, or one file in the directory, to create an NNEF with the following command. If I use this command, which also quite self-explanatory, I will explain soon what does it mean. So Python 3, NNEF tools, convert.py, input format TensorFlow-py, which means that it's not a saved, but it's really a Python format description of the file. Output format NNEF. Input model, I specify tf underscore AlexNet, and I also specify the checkpoint file, the second one. I also require some conversion information to be printed out, and that's it. Let's see, hopefully it works. Yes, it's done. It printed out some debugging, and also TensorFlow have been imported, and that's why this lot of message appeared. That has nothing to do with the NNEF, it's just TensorFlow debugging information. And an AlexNet NNEF conversion.json, this is the conversion info that have been generated. If I want to save the weights and the activation, then I can use that command. Let's go through on that. In this format, it is easier. So export activation, use this format, TensorFlow Python format. Input model is the same, AlexNet, and its checkpoint. I specify the conversion information which have been saved by the previous command to this file, to the JSON file. Output paths, AlexNet.NNEF activations. And if I execute this, then it also works. So let's see. AlexNet.net. That was the output directory specified. And in this directory, you see the graph.NNEF, the NNEF format, AlexNet network architecture descriptor in a text format, and also the weights, the data parameters have been exported. This is the binary file. It's not really interesting. So all the tool has this maximum, this level of complexity. It's really easy to use. What is missing in my sense still, or can be improved, is really the different kind of visualization, cross-checking, sanity checking, validation, helpers functionalities, but those are also on the way. And the conformance test will, of course, be very, very interesting, also by the by the software developer, so what kind of precision, what kind of accuracy one can expect from a specific hardware, a specific inference engine, and it will be interesting. It will be kind of benchmark for the inference engine providers, manufacturers, to really comply with this standard. I think I stop now because I will just repeat myself. So if you have any question, I'm happy to answer. If not, then thanks for your attention.
I have a question for you. Sorry. Okay. So thanks for the talk. And so for NNEF, the primary goal is to ensure portability across, right? So you write it in NNEF, and you can run whatever you support NNEF. But the reality is all the innovation is coming from above you, right? So it's coming from different frameworks. People are developing in different frameworks, and those are changing very fast. So for example, even for Onyx, one of the problems is that lots of the operators that people now use are not supported, and you see constant effort there to enable them. But NNEF, by your presentation, is designed to not change fast. So how do you resolve? I mean, it still makes the problem not resolved for vendors that are trying to support NNEF.
I think this is a very good question, but this is not really NNEF specific. So this is valid for any new standard, for any compute language or compute programming language, or any new standard that you introduce, because a new field is emerging. The field is still evolving a lot every week, every month, just as you are saying. But you have to somehow arrive to a baseline understanding, common understanding. What are the features that will be supported on the long term? What are the features that the hardware manufacturers should or must support? So I think it's always a compromise. You are absolutely right. NNEF is not because of its architectural design or because of its conceptual design, but because of its governance policy, not yet supporting all the new fancy functionalities. So we don't want to update NNEF every month. We could do so, I think, but that would put us in danger that we put things into the specification which are not yet mature enough, or will change, or will be forgotten in 1 month. So I think this. I think the people in the room has much more experience in maintaining standards than me, but this is this question is not NNEF specific. Yeah.
That's true. It also eats into the portability, right? So what the customers or developers are looking is, say, can I train in standard framework, develop a new model, and can I port it to different hardware that they want to run into? It kind of defeats that purpose, because it comes to the same common denominator that different hardwares are not portable, and you have to program differently for them.
I don't see this. I don't see that it limits portability. It limits maybe the feature set. So if there is 2 hardware, each of those supporting NNEF 1.1, then portability is there, and that was the goal. And that hardware will not change in 6 months. The hardware is not changed. You cannot just update it like software. So once an embedded inference engine supports a specific version of NNEF, then it will support that for a lifetime. And that was the goal. So I think portability is maintained.
Cool. Thanks.
Thank you. Yes, please.
Can you name one engine right now that supports NNEF?
Yes, just behind your back.
What is it?
Thank you. That's AI motive inference engine called AIVer. That's a proprietary IP the company has developed. And we are using that IP to replace the GPUs in the trunk of our test vehicles. We also developed the driver, the software side, the driver, and the inference optimizer. And that uses as an input the NNEF descriptor of the, for example, in this case, the free space segmentation neural network, which is running on a reversing camera, and produces the execution graph for the hardware. I don't know yet about other. Yes, yes, sure. I was not sure whether those are already in production, but definitely, yes. Thank you.
Which one is that again?
MI Vision X, the tool which we're going to talk about.
Yeah.
Supports NNEF.
Thank you. Thank you very much.